So in today's lecture, we are going to continue with the chapter of discrete time signal and systems. There are 5 parts I want you to know from this chapter. The first one is discrete time signal. The second is what is discrete time system. Then analyze of a discrete time linear time invariant system. Understand the concept of a linear time invariant system. Then the fourth is implementation of discrete time system. And the last is the correlation of discrete time signals. So what is discrete time signals? Let's look at some elementary discrete time signals. Now I will call those building blocks of discrete time signals. Very simple one. The first one is the unit sample sequence. Unit sample sequence is a delta function, or people also call that direct delta function. It's specified for the discrete time signal. Delta function is I have a signal delta n when n equal to 0 have a value of 1. And it's a 0 elsewhere. So here, we know it's very simple. Signal looks like this. It's just one finite spike of 1 at time equal to 0. This is time n. Delta unit sample sequence. Now we have used that when we do sampling, we're actually using a delta train, or whenever we have a delta function on this time stamp, and that's the sample we are going to take. What I meant is here, if you have a delta n subtract whatever the, let me just kts, because this is our sampling period, k is an integer. Anytime you multiply this to your original signal, what you did is you take a sample. Okay. And the second one is unit step signal. Unit step signal is look like this. So when it's greater than or equal to 0, you give me all ones. And all the negative part, negative time, the signal is 0. So that is unit step function of un. Now, when do we need this signal? Later, we will know if we are talking about a causal signal. Causal signal is signal that is only has a positive value from current to n positive. So we are going to use the unit step signal multiplied by xn, arbitrary xn, and then you got a causal signal. Unit to ramp signal. Unit to ramp signal, you can look at that as a linear signal, but it's only half of my plan. It's starting from 0, and it's just going upwards. Right, this is unit ramp signal. And then the fourth one, exponential signal. Exponential signal is actually quite useful because those are the harmonics, or those are the frequencies that we need. And each exponential signal, a to the power n, then this a is a complex number. We can represent it using its polar form. So r times e to the power j theta. R is the amplitude, or the mole. Theta is the phase to the power n. So we got those two parts in a polar form. That's the exponential signal. Exponential signal, in this case, we have a signal that is, this is my exponential part, and that is its amplitude. Some different classifications of discrete time signals. An energy signal versus power signal. The energy of a signal is expressed like using this formula. So the energy is signal xn, absolute value square, and then sum over the entire time span. Now, if I'm doing this, then I know that xn, absolute value square, this is called the power of the signal. As instantaneous power, that's the power of the signal at time n. If x is a complex number, if it's a complex signal, so this part will be xn times xn conjugate. And then this is the instantaneous power. You sum over the entire time span, that's the energy. If the energy is finite, then xn is energy signal. Okay. Now, if I have a sine wave, this is time. Is time wave an energy signal? Well, apparently not, because if you sum over the entire time horizon, it goes forever. It's a periodic signal. Therefore, your energy will not be finite. Power of a signal, P is you take this energy, this is the energy part, divide by the time span. So if this energy you only measured from negative n to n, then divide by the time span, which is 2n plus 1. And the power is for the entire signal, n approaching infinity, and you find the power level. So if E is finite, if energy is finite, P is equal to 0, because n is approaching infinity. If you have an energy signal, this is finite, and then P is 0. If P is finite, and we call the signal a power signal. So a cosine signal, any periodic signal, is a power signal. Periodic signal versus aperiodic signal, that's easy to understand. If it's periodic signal, then I will have a period. In this case, a period is time index capital N, and the smallest n is the fundamental period, because 2n, 3n is also its period. So this is the period of this n here. For example, a sine wave, a cosine wave is a periodic signal. The power of a periodic signal is we can just look into one period of n. You sum over the signal, instantaneous power, over one window of n. It doesn't matter. As long as this window length, the window span is n, divide by n, and then you got a power. Therefore, any periodic signal is a power signal. Symmetric versus anti-symmetric signals, or even an odd signal. This is even signal. Even signal is a mirror around the y-axis. This is odd signal. Odd signal, you can think that's a kind of a flip or the mirror around the original point. Any signals can be expressed using this as an even plus an odd signal. So this is an even signal. This is odd signal. Any signal can be divided into an even plus an odd. To prove it's very simple. You are using these half of this and half two of subtract. Now we know some of the fundamental discrete time signals and the basic classifications of signals. Let's look at how we can make this signal work, how we can manipulate these signals. There are some of these common of simple manipulations in signal processing. The first one is time delay. Time delay is I'm taking signal xn and delay by k sample period. And you can think that as I have a memory unit. I store that after k sample period, and then I release it. So we have the delay xn of k. So the time delay is I have the signal called xn subtract k when k is greater than 0. And of course, k is an integer. If k itself is a positive number, now if I have this n plus k, if that is also a valid manipulation that we call a time advance. So instead of with delay the signal, we kind of look into the future of this signal, or the future of this input. Theoretically, we don't have that yet, right? It's the future input to my system. I don't have it yet. It's called time advance. The second one is called time folding, or the time reversal. So just you check the signal from future to present to past. Amplitude scaling, or it's also called amplification. So we have a signal, you just go through some op amps with an amplitude of A, and then you amplitude scaling. Now A here can be a real number. It can also be a complex number, as long as it's a constant. Okay, I multiply something and give me the output, the scaling. Sum of two signals are sample-wise addition. On each end, sample-wise addition. Product, this is a sample-wise or sample-to-sample basis productions, x1 times x2 on each sample time n. Discrete time system is the operation on a discrete time signal. And we are using an operator called a T. Any operator, you're working on xn, you're going to yn. So the input signal is discretized, going through a discrete time system, and we got output signal, yn. And this is the part, discrete time system is something that we need to design or we need to analyze. Input output of a system, and I'm writing this again. This is xn, go through the system. The system is t, and then we have the output yn. Also, you can write this in this format. For example, if I have an accumulator, so I can model this accumulator using this difference equation. We call this difference equation. We sum the input xk, k is from negative infinite to current time n. We got yn. So what we are doing is that I take the input signal, but it's accumulation of all the past input and add the current input. And then we got the output yn. So it looks like this. Right? If you write this out, it can be spread like in this form, the second line. Look at the second line. What we can do is I can leave one xn here, and then the rest. Okay, this looks as if I am doing this and becomes yn minus 1. Right? So yn minus 1 equal to that. The only change is I'm changing time index from n to n minus 1. It's that. So it becomes yn equal to yn minus 1 plus xn. So this is also a kind of a difference equation. In general, this is difference equation. So this is also a difference equation. n minus 1, yn minus 1, it's just a delayed version of the output signal yn. It delayed one time instant, or sample time instant, and yn minus 1. We find it's if you write it into this form, it's relatively simple. I don't have an infinite many term to sum up. So the same thing, the same accumulator, I can implement it using these two different approaches. The first one is the naive approach. I just get input every time. When I want to give you the output yn, I need to check all the input, current time and all the past, and add them together. The second approach here is I don't need to check all this input. Every time I need to provide you with yn, I can just adding the current input onto the memory. The memory is the previous output, right? I memorize that, putting a memory register and added x0. It gives you exactly the same effect as you do this accumulation. If the system is relaxed, initially relaxed at n0, for instance, n0, that means at time n0, I'm checking with the system memory, it's all flushed to 0. Okay, let me say it again. It comes from here because when I mention I can implement that using just a memory, right? This memory is to memorize whatever the previous output at current time n, so it's yn minus 1. So if this memory is all zeroed, and we call that initially relaxed. So if I want to say the system is initially relaxed at time 0, that means y negative 1 equal to 0. Because I only need one unit to memorize, so it's y negative 1. Later we know we may need yn minus 2, yn minus 3. So at this time, yn minus 1, yn minus 2 should be equal to 0. It's called initially relaxed. This is the block diagram representation of discrete time systems. The first one is an adder, sample-wise addition. Constant multiplier. You can use a op-amp or simply put a weight on this line. Understand that this is the gain. Signal multiplier, this is sample to sample multiplication, x1n, x2n equal to yn. Unit delay element and unit advance element. Unit delay element is we put in z to the power negative 1 here. A unit advance element is a part of z to the power positive 1. What do you think about this? xn. Well, naturally, you'll think that should be equal to xn minus 2. Yes, indeed, that's a delay with 2 time units, 2 time samples. You can break that into two parts. Let's see, delayed and delayed. Okay, so yeah, and that is very well understood. So we have a delay in this case. People may ask me, why do I use z here, z to the power negative 1? When we look into the z transform, you will see the clear relation here. Because in z transform, what we do is when you multiply the signal by z to the power negative 1, that will be a signal, it's a z transform of signal x n minus 1. Now let's look at some classification of systems, classification of discrete time systems. And different classes. The first one is we check the difference between a static versus dynamic system. Static system is a memoryless system. Static system looks like this. It's only taking the current input, So the current input is xn, give me yn, xn squared, give me yn. On the other hand, the dynamic system is I have the system that I'm only care about the past input, This is xn when k equal to 0, and then xn minus 1, xn minus 2. We call that a dynamic system. Usually, we are dealing with a dynamic system. Static system is memoryless. Memory system represent only a very small part of the phenomenon or of this operations in the engineering world. So we're using the dynamic system. Time invariant versus time variant system or time varying system. A time invariant system defined as this. So I have an operation xn becomes yn. That implies xn minus k give me yn minus k. K is a constant. It's an integer constant. So what it says is that the system itself does not change. It's not a function, the system parameter is not a function of time. So the system you check today, tomorrow is the same. You can give me exactly the same input, I'll give you exactly the same output. Okay, so a lot of systems in the engineering world is time invariant because it's really itself, the property or the feature of the system itself does not change, does not depending on n. You can write this yn output. First of all, it's a time series, so it's a function of n. Second, k, this is so-called delay, which is you can think that as absolutely, this is absolute time. This offset to the absolute time is delay. As we said, we are only care about the relative time. So that whenever the time you observe, subtract this k. This is the relative time. We only care about that. So its representation can be simplified as yn subtract k. I only care about the relative time, delta n. Now remember this, the last line. We're going to use that to analyze a linear time invariant system. Linear time invariant system, the second part, or the first part I should say is important, is that it is a linear system. It's a linear and time invariant. Okay? So we look at the linear. What is linear system? We know linearity mathematically is just a straight line or straight segment. If you look at a system, it tells that the system should follow this superpositioning law. I have a signal x1 and x2. If I am combining these two signals, adding them together, and it's a weighted combination. So I weighted by alpha 1, it's a constant. Here's alpha 2 multiplied by x2. Then you go through the system. It should be as if you take each signal, go through your system, and then weight it, and then combine it. Right? So you can take this operation into this bracket and work on each individual signal, x1 and x2. So the superpositioning law, including two parts, the scaling multiplicative property and the additive property. So we see using the block diagram. Now this is combination of two signals, x1 weighted by a1, add x2 weighted by a2. or alpha 2, and then this is combined signal go through my system, give me yn. If the system is linear system, that means I can use a system on each individual signals and then weight it by alpha 1, alpha 2, adding together, give you another output y prime. Y prime should be equal to yn. That's the linear system. Every system that follow this law is a linear system. Now it can extend to many of those inputs. It can actually extend to infinite many of those inputs. What is a causal system? When I show you the unit step function, I mentioned that sometimes we call a signal causal, we call a system causal. So called a system causal is much easier to understand. From common sense, we can understand what is a causal system. Causal system is saying that the system output only depends on the current input and the previous input, which makes sense, right? In the physical world, that's what you get. You are not going to look into the future input. It's not arrived yet. You're only looking at the current input and the past inputs. So the transformation of xn, xn minus 1, xn minus 2, and if it goes on, and give me the current output. That is a causal system. Stable versus unstable system. A system is called a stable. More specifically, it is called a bounded input, bounded output stable. If and only if all these, given all these finite input, so each input xn is a finite value. Absolute value is less than or equal to capital M, which is a finite number. Then the output is finite. And then I call this a BIBO stable. Well, if I have all the input is a finite number, then output is a finite number. That is easy to understand. Should all the system look like that? Or when will it be unstable? Unstable by definition is saying that if you're dealing with all the finite signals, somehow you will get an infinitely large output, and then basically your system just blew up, and you have an unstable system. What are the cases that I have a system that is unstable? We got a bounded input, but somehow I got an unbounded output. The output is infinitely large. One answer is the previous example I give you, which is accumulator. Accumulator is adding infinite many things. I'm adding current input and infinite many previous output. So even though each one of those elements of xn can be a finite number, but you are adding infinite many terms. So there is a possibility that the output yn will be infinitely large. And that will give me an unstable system. If we look closely with the difference equation yn, remember that we changed that to this, right? We changed that to this, xn. So this indeed kind of give us some potential problem, because I have this term. This term we know we call that a feedback term. So you got an output, but somehow you count this output again, even though this input every time you got xn, it is finite, but because you have this feedback loop, kind of a feedback loop, it's feeded all the time, and it may make your system unstable, right? So we have the stability issues here.